In this video, we look at how the orbital and the spin angular momentum can be added to give the total angular momentum. So far, we have characterized each stationary state of the hydrogen atom with the four quantum numbers n, l, ml, and ms. In addition, we have s equals 1/2. These quantum numbers mean that the orbital angular momentum and the spin angular momentum are conserved quantities, separately. Now, the spin-orbit coupling results in an interaction between the two, between L and between S. This has the consequence that ml and ms are no good quantum numbers anymore. However, the total angular momentum of the atom must still be conserved. The total angular momentum vector is indicated by J, and it is formally the sum of the orbital and the spin angular momentum vectors. I've put hats on to indicate these are operators in quantum theory. The properties of J are similar to those of the other angular momenta. The eigenvalues of J squared are h bar squared times J plus 1. And the eigenvalues of Jz, a projection along an axis, are equals to h bar times mj, where mj runs from negative j all the way up to positive j. This is the total angular momentum. We know the values for mj, but now we need to find out what the possible values for the quantum number j are for a given L and S. For this, we first obtain all possible mj values by adding the possible ml and ms. According to mj equals ml plus ms. For a given L, there are two L plus 1 possible states, and for S, there are two possible values of ms, so in total, we have 2 times 2L plus 1 total states. For example, let's look at L equals 1, and of course S equals 1/2. This would correspond to a p state in a hydrogen atom. We have 2 times 2L plus 1, which is 3 times 2, a total of 6 states. M sub L can be -1, 0, or +1, and M sub S can be positive or negative 1/2. Let's classify the states in terms of ML and MS combinations and make a table of the possible MJ values. The highest MJ is 3 plus 3/2. It is obtained with ml equals 1 and ms equals plus 1/2. Next, mj of plus 1/2 can be obtained two ways, either with ml equals to 1 and ms equals to negative 1/2, or with ml equals 0 and ms equals plus 1/2. Next comes negative 1/2 for mj, which can be obtained by ml 0 and ms negative 1/2, or by ml negative 1 and ms positive 1/2. Last, we have an mj of minus 3/2. And the only way to get that is with an ml of negative 1 and an ms of negative 1/2. Now we have classified all the combinations ml, ms in terms of mj. Which j values are possible? The reasoning is the following. The highest mj is plus 3/2. So there must be a j equals 3/2. Now, for j equals 3/2, we'll have an mj of 3/2, of plus 1/2, negative 1/2, negative 3/2. So we take out one state in each row. It doesn't matter which, since this is just a counting aid. We are left with two states. The highest remaining mj is plus 1/2. So there must be a j equals 1/2. For j equals 1/2, the possible mj values is plus 1/2 and negative 1/2. So we take those two out from the table as well. So now there are no more states left. We're done. Overall, we found that the 6 states with L equals 1 and S equals 1/2 lead to a set of 4 states with J equals 3/2 and a set of 2 states with J equals 1/2. We can summarize this in a rule for the addition of angular momenta. For one electron, the rule is the following. The possible values for J are L plus S and L minus S. Norm. For many electrons, the rule is more general. The total angular momentum quantum number J can be L plus S minus 1, all the way down to the norm of L minus S. Here, the uppercase L is the sum of the orbital angular momentum quantum numbers of all electrons, and uppercase S is the sum of the spin angular momentum quantum numbers of all electrons. The one electron rule is just a special case of the many electron rule. Generally, we use uppercase letters to distinguish the many electron case from the single electron case. So, in the presence of spin-orbit coupling, the good quantum numbers are L, S, J, and Mj. There is a dedicated abbreviation for such states. 2s plus 1, letter X, J. These symbols are called term symbols. X is an uppercase letter that encodes the quantum number L. For L equals 0, the letter is uppercase S. For L equals 1, it's uppercase P. For L equals 2, it's T. L equals 3 is F. And so on. The pre-superscript is called the spin multiplicity. It is the number of spin states. For a single electron, S equals 1/2. And the spin multiplicity 2s plus 1 is 2, since there are 2 spin states, spin up and spin down. This is called a doublet. In many electron atoms, states with spin multiplicity other than 2 are possible. If the multiplicity is equal to 1, they're called singlets, and those states with spin multiplicity 3 are called triplets. Each of these symbols represents a group of states with specific L, S, and J. In each group, there are 2J plus 1 states. Here are a few examples. The 1s configuration of the hydrogen atom gives rise to a 2s 1/2 level, doublet s 1/2 level with 2 states. The 2s configuration gives also rise to a doublet s 1/2 level. The 2p configuration gives rise to a doublet p 1/2 and a doublet p 3/2 level. The doublet p 1/2 has 2 states and the doublet p 3/2 has 4 states. So in total we get 6 states, as we should. Due to spin-orbit coupling, these 2 groups of states will have different energies. In summary, due to spin-orbit coupling, we have to take the total angular momentum J into account. The possible values of J can be obtained from a general addition rule for angular momenta. And lastly, term symbols are used to designate these states.